Morning, nerds. Today we are going to officially start Unit 2 of the AP curriculum, and that's why I've called it 2.1a. If we were still following our textbook, we'd officially be in Chapter 3, but we're going to follow the AP curriculum order because then I could better utilize AP Classroom. So, this unit begins with sequences, specifically change in sequences, like rates. Change in tandem, when is the graph decreasing at an increasing rate kind of stuff. Change in tandem. It's a pretty big deal to the AP people. But even more specifically, we're talking change in two very kinds of special sequences. And those are arithmetic sequences and geometric sequences. Not arithmetic sequences. No, arithmetic. There is a difference. The word arithmetic is a noun. Today we're going to practice some arithmetic. That's a noun. This sequence can be described as an arithmetic sequence. There's a difference. You might be thinking, what's the difference? Why does it matter? Okay, let me ask you. Who do the people do you live with in your house? Oh, did I say that wrong? Oh, I meant live. Oh, you see how it's spelled the same, but we pronounce it differently depending on the situation? This is one of those times. Like, one of my favorite things to do is read a book. See how that sounds weird? Even though it's spelled the same, we say it differently based on the situation. This word is arithmetic when you're using it as a descriptor. Okay. Now that we've got that out of the way, let's talk about what something is when you say it's a sequence. A sequence is literally just a list of numbers that follows a pattern. If it's a sequence, you should be able to predict the next term. Okay? We number the terms in a sequence as the first term, the second term, the third term, the fourth term. We literally count them. This is the first one, this is the fifth one, this is the 12th one, so on and so forth. This is a very famous sequence called the Fibonacci sequence. It is neither arithmetic nor geometric. It is just a sequence that follows a pattern. And in case you don't know what that pattern is, it starts with 1, 1, 2. And then every term after that, actually it starts with 1, 1, and this could be any number. But after that, you add the previous two terms to find the next one. So 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, so on and so forth. Cool beans? That's what the Fibonacci sequence is. And it does a lot of really neat stuff. But look, can you discover the rule for the next term? I already ruined that for you. I already told you. You add up the two previous terms to find the next one. But that causes us a problem. Because what if I asked you what the 15th number in the Fibonacci sequence was? There's actually not a way to just know what it is when I told you needed the 15th term. The only thing you could actually do is build all the way through the 14th term and then add the 13th and 14th terms to get the 15th. And that kind of bothers us a little bit. We'll talk about that more in a moment. So I've already kind of defined a sequence for you, but the official definitions that are in the notes, an infinite sequence, see it's bold, an infinite sequence is a function. Ooh, a function. That's why we're talking about change, rates of change. An infinite sequence can be modeled by a function whose domain is the set of positive integers. That, ladies and gentlemen, is a big deal. Domain is the numbers that we plug in, right? I'm telling you, for it to be a sequence, specifically an infinite sequence, but for it to be a sequence, you were only allowed to plug in positive whole numbers as your inputs. Why, Mr. Rem? That's a fantastic question, Squeaky. Let me tell you why. Because as you guys walked into the room today, I could have listed you as a sequence of students. That's the first student, that's the second student, that's the third student. You know what I couldn't have said? That's the 3.5th student. That's the 2 1/4th student. It only makes sense that whole students came into my room or did not. Okay, this is not a horror film. Either whole students come in or they don't. We call this discrete mathematics, that there is nothing that exists between the terms. There is the first one, the second one, the third one, the fourth one, so on and so forth. So this is discrete. And that's why we say positive integers. I can't say the -1th student. That doesn't make any sense. I also technically can't say the 0th student. That, again, makes no sense. We'll talk more about that in a moment. Yes?
But negative numbers don't make half a student, right? Like if
No,
I left the room, would that?
no. What we're talking about is the input values of the sequence. So again, remember, it's a list of things. So you can't have the negative turn. That doesn't make any sense. It's either the first one or the second one or the third one. It's a list of terms, and we're literally just counting them. Now, here's another thing that we could talk about. We've already said the word terms. We have the values of the function, or its term values. Those are like the y values, the outputs. So our inputs are term numbers. Our outputs are term values. And another thing that makes it infinite sequence is that we literally can't count them all. It goes on forever. And that's what the ... tells us. That means that never stops. However, if the domain of a function consists of the first n positive integers only, meaning you could actually give me a number, the first 100 positive integers. If you restrict the number of terms and say, oh, there's only going to be 50 terms, this is now a finite sequence because you could count the number of terms. So infinite means it never stops. Finite means it comes to an end. Again, something that's pronounced differently. It's infinite, finite. See how they're pronounced slightly different depending on the context? Okay. Jack W., you had a hand up a minute ago. What's up? Why do people say stupid oh, I almost said a bad word. Stuff. Were you a whole person in the room yet? No, then you are not on the list of students that have entered the room yet. If you are not in the room yet, you are not in the room yet. You are either in or you are out. I said you are either in or you are out. You are either in or you are out. I'll keep saying it until you just agree with me. You are either in or you are out. Okay? Okay. You are either a whole person in the room or you are not a whole person in the room. Those are the only options. This is a yes-no situation. Yes, no. What did she say?
I said it's like a Boolean. It can either be true or false.
Ooh, that is a big math word you just used right there. You've been doing research? Coding, yes. There's a ton of sequences in computer programming. And by the way, the word she used was Boolean. It's a big deal. Fibonacci code? Right, but the way that you told, the computer did the math. So when you wrote the program to give you the Fibonacci numbers, you told it you're going to have to add the 2 before it. So if you asked it to find the 50th Fibonacci number, it crunched all the numbers and found the 48th and the 49th one, which is incredibly processor heavy. It probably used up a lot of memory too. Did you have to do any memory allocation, or do you not have to do that? Oh, okay. So when you learn a more difficult programming language like C++, you would find that you have to do things like memory allocation, and that program that you wrote uses a lot of memory, and it would bog the system down because it had to do a bunch of crunches to get there. Okay, it's like when we do our graphing calculator and we give it something really difficult to graph, and that little yellow thing spins forever and ever and ever while it's graphing. That's because it's doing number crunching. Yeah. The Fibonacci sequence, the limit of the ratio of the Fibonacci sequence of any term divided by the one before it is the golden ratio, but yes. Anyway, back to this lesson because we have a certain point that we have to get through today. Guys in the back, they can hear me, right? Just making sure because they're all staring at each other or something back there. I'm not sure. They're doing something on their calculators. Anyway, academic vocabulary that you must know. The nth term. If I say the nth term, I'm literally saying a sub n. The nth term, meaning I don't know which one it is. Is it the 5th term? Is it the 8th term? Is it the 105th term? I don't know. We can also call it the general term, which will often be how we get our equations, what we're calling our functions, our models for the sequence. Sometimes the letter K is used instead of the letter N. I'm going to basically only ever use the letter N, where N stands for the term number. You know what? Let's go ahead and write that. See where it says term of a sequence? which I'm going to say n is term number, where a sub n is the term value. For example, if you went up to the Fibonacci sequence, I could say, what is the 6th term in the Fibonacci sequence? And you would go up to it and you would literally count to the 6th term. 1, 2, 3, 4, 5, 6. A sub 6 is 8. That means the 6th term, a sub 6 is 8. The 6th term has a value of 8. So that's the difference between a term number and a term value. Okay? Big deal that you understand that. And I've already told you that a finite sequence means that we can tell you how many terms it has. And that's kind of also a really big thing in mathematics, which when we get later into the lessons, I'll be able to tell you stuff like, what is the sum of the first 100 positive integers? You see, the positive integers are a sequence. They go 1, 2, 3, 4, 5. Their pattern is +1 each time. And there's a way to figure out the sum of the first 100 or first any number of whole numbers. And it's actually pretty quick. The sum of the first 100 positive numbers is 5050, 5050. Okay? And I just did that using a math trick that I know that I'll teach you later in the unit. Okay? Generating a sequence using an explicit formula. All right, well, let's talk about this. More academic vocabulary. Explicit in mathematics does not mean what it means in regular words. When you say something is explicit, normally you mean like it's crude or it's vulgar. Like bad language is explicit language. That's why it's called an expletive. Okay. In mathematics, when you say it's explicit, what that means is all you needed to know was the term number. All you needed to know was n. You could use that as your input, and your output would be the term value. So just a moment ago, I had a conversation with Isabella about her program. The program that she wrote for the Fibonacci sequence is not an explicit formula. It literally said, you're going to have to add up all the numbers, you're going to have to get there, and then eventually you're going to have to add up 48 and 49 to get to the 50th one. That kind of formula is called recursive. And recursive formulas are a big deal in computer programming. So I'm glad you brought that up. In second period, I just said that statement, but none of them programs. So, and to be real with you, recursive formulas, or computer programming, recursive formulas for computer programming is about the only place that I know of where recursive formulas are actually a big deal. I don't know of any other places. Yes, Adi? Yeah, eventually. But it's not part of today's lesson. Eventually, I'll teach you. So explicit means if this is an explicit formula. It says if I know the term number, then I can find the term value. So it says, hey, find a sub 12. Here's what that means. That means n is 12. So I'm looking for the 12th term of my sequence. And orange, might as well write in blue, go Gators. So a sub 12 is 12 times the value of n, which was 12, plus 3. It's 144 plus 3. There. The 12th term of this sequence is 147. And this setup should look familiar. If you'd watched the video last night, you probably already know exactly what I'm talking about. But a y value that was generated by multiplying to your input and then adding something to it should look very, very familiar to you. Any ideas? Slope-intercept form. Sure looks like y equals mx plus b to me. Interesting. Does that mean all sequences work like that? Nope. That one did, though. Very interesting. Oh, by the way, since we did mention slope-intercept, what is the first term of this sequence? $15 is the first term of the sequence. How did you get that number? Plug in n equals 1. Do you know what some people might have said and is absolutely the wrong thing to say? 3. You only get 3 if n is 0. But there is no such thing as the 0th term. Yeah? I won't ever ask for the 0th term. I mean, can you imagine that it would have been 3 if it was such a thing? Sure, but it's not. There is no such thing as the 0th term. Are there times when it's useful to imagine what it might have been? Yes, but I am never going to specifically make you give me that as an answer because it's not a true thing. Okay? Just like there are no negative-th terms. It just doesn't make any sense. In a list, the first thing is the first thing. It's not the 0th thing. Okay? Okay, so for example 2 here, A and B, it says write the first 4 terms of each sequence. So I'm going to be plugging in n equals 1, 2, 3, and 4. A sub 1 is 3 times 1 minus 4. Well, 3 minus 4 is negative 1. A sub 2 is 3 times 2 minus 4. That's 6 minus 4. A sub 3, okay. Oh, I wrote it in purple. Shucks. You can't tell? Are you colorblind? You can't tell the difference between those two colors on the image, on the screen up there?
Not much.
What? Those are drastically different. You guys are colorblind. Yeah, between the red and the purple.
Oh, the red and the purple, yes. I thought you were talking about like blue and I thought that was okay, I'm sorry.
No, it's red and purple. Look, you guys are crazy. You can easily see the difference between those numbers.
Honestly, I might need glasses.
Glasses have nothing to do with color perception. And 9 minus 4 is 5. And if you haven't noticed yet, there's a pattern here. Look. Ooh. It goes up by 3 each time. I wonder why. No, it's not arithmetic. It can be modeled as a linear function, though, which makes the sequence... Oh, shoot, I wrote 3. Which makes the sequence arithmetic. So I'm going to cheat a little bit and clue you in. An arithmetic sequence can be modeled by a linear equation. Yes, that's what makes it arithmetic, is that it can be modeled as a linear equation. Well, we'll get to geometric. We'll get there. We don't want to spoil it for anybody because they're going to watch the videos over the weekend and spoil it for themselves. Yes. Anywho's it. This next one, we're going to do the same thing. We're just going to plug in the numbers 1 through 4. And let's do, ew, yuck, don't tell my wife. I'm going to write in orange and green. What did you say, Jack W? Why would I just plug in 3? What? Because it says write the first 4 terms. I'm just following the directions. He's asked me why we follow the directions. No. Sometimes you have to generate your own formula. So this is 5 minus 1. Negative 1 squared is positive 1. So this is 5 plus 1. Let's be really clear here. 2 terms of a sequence is never enough to see a pattern. That's never enough. Minimum 3. No, it's a serious question. Minimum 3.
Like science, you gotta do 3 trials.
Yeah, the more trials you have, the better off you are.
Look at me, I'm killing you with 3 hours today.
I know, she's on point. Negative 1 to the third is negative 1. So this is 4 again. We can probably see our pattern. Probably. But negative 1 to the 4th is positive 1. Oh, okay, I think it's obvious what the pattern is. It's just oscillating back and forth between 4 and 6. Do you remember when well, no. It's not wiggly because we can't connect the dots. We can't connect the dots because remember, there is no such thing as the 1.5th term. So the dots cannot be connected. They're what we call discrete data points. So if we were going to do that, like here's one. Here's one. You can't connect these dots with a line because that would imply that I could plug in the number 1.5, but I cannot. So sequences can only be modeled as dots. We can never connect them. So the one we just did, and just imagine there's no red there. The one we just did does this. 4, 6, 4, 6, 4, and it just bounces back and forth, and that's why we call it oscillating. Because no matter what, the return value is always going to be a 4 or a 6. Yes, Adi? The sum of the first 100 digits is 5,050. No, 5,050. 5050. Yes? Oscillations, as far as I know, will only ever oscillate between two numbers. And actually, that's something I want to mention to you. Earlier in the year, when we were talking about the types of discontinuities, I taught you about infinite discontinuities, I taught you about jump discontinuities, and I taught you about removable discontinuities. There's actually a fourth kind called an oscillating discontinuity. And it does exactly what the sequences do. It literally oscillates between two numbers in mathematics, and often there'll be like a -1 and a +1. And it's as you get closer and closer and closer to, say, a number 0, what ended up happening is, I can't think of the exact equation right now because I'm not as big a nerd as I thought, is you end up getting graphs that'll do something like this, and you put them on Desmos, and you see it do like that. And it's like, and it doesn't matter how close you zoom in, it's always doing this on both sides. And those are not discrete, but you'll never actually be able to get towards the 0 because on one side of the 0, it'll be a +1. On the other side of the 0, it'll be a -1. And we call that an oscillating discontinuity. No, it's not an asymptote. It's an oscillating discontinuity. It's literally a y value where we couldn't tell you if it's a +1 or a -1 there. Oh, the sequences don't have asymptotes. Neither. It's just a sequence. Yeah, you mean is it arithmetic or geometric? It's not. So sequences are either arithmetic or geometric or neither. This would be a neither.
So B is neither, then A is arithmetic.
A is arithmetic, but arithmetic, yes. So now this says find the first 3 terms, which we're going to do the same thing we did here, where we just plug in the numbers 1 through 3 for n. But then we're going to use our explicit formula to find the 11th term. Not bad, not bad. Oh no! That's supposed to say -1. Shoot, fire. So we're letting A be, or n be 1, 2, and 3. 1, 2, and 3. Well, 1 minus 1 is 0. 0 times 5 is 0. So this is just a sum of 4. But then here, 2 minus 1 is 1. 1 times 5 is 5. So 9. Interesting. It went up 5. How about that? And then 3 minus 2 is 2. 2 times 5 is 10. 4 plus 10 is 14. Interesting. It went up 5. Oh, I know why it's going up by 5. Look at this. I could distribute that 5 right there. And this would actually be written like this. If I wanted to do that, I could say 4 plus 5n minus 5. And 4 and -5 are like terms. So I could write this as 5n minus 1 if I wanted to. I would just have to remember that n is greater than or equal to 1 and can only be whole numbers. But I could write it just like that if I wanted to. Which looks, again, like y equals mx plus b, doesn't it? Where m, the slope, would be that multiplier. Interesting. That's so interesting. Okay, let's find the 11th term. And it doesn't matter if I use this formula or this formula. It's the same thing. I'll use that one because it looks easier. Let's figure out what a sub 11 is. 5 times 11 minus 1. 55 minus 1? 54. There it is. Boom, baby. A sub 11 equals 54. The 11th term of the sequence has a value of 54. So I've actually already cheated. I've already been using the terminology of arithmetic, and I've already explained to you when we recognize it as arithmetic. The back of this page is about arithmetic sequences. Can I flip the page? Okay. Flip them. Arithmetic sequences. So what defines an arithmetic sequence officially? Arithmetic sequences have the same differences between the terms. That means you are either adding or subtracting the exact same number every single time. Adding or subtracting every single time. And that number that we are adding and subtracting every single time is called the common difference. Now, difference in mathematics means what? Subtract. The reason why it's called the common difference is because the common difference can always be found, if it's arithmetic, by taking any term and subtracting the one before it, which is literally what this is showing you. The common difference is second term minus first term, or third term minus second term, or fifth term minus fourth term, so on and so forth. The common difference is any term minus the one before it. Sometimes that's positive, sometimes that's negative, but it's called the common difference because we find it through subtraction. Are you comfortable with that idea? Yes? Great. So let's write the explicit, also known as the general term, also known as the explicit or general form. A sub n is a sub 1 plus, I don't like the way they've written it here. I like n minus 1 times d. Let's just talk about what they've done here. N minus 1 times d. So explicit means the input is the term number, the output is the term value. That's what explicit means. It means I don't need to know any other prior terms. I don't need to know any other terms to get a term. That's what explicit means. Now let's just talk about what you're looking at here. In general, the best way to do these is know the first term. That's the best way to do them. But let's say I gave you the fifth term and the eighth term. Technically, you don't need the first term because you know the fifth term and the eighth term are 3 apart. So then you could just utilize that knowledge to say, I need 3 common differences. So you don't actually need to know the first term. I'm in the habit of always finding the first term, though, because of IB mathematics. So I typically will go to here first. And it won't matter if you do or not, but I will always do, bless you, I will always do this. Does that mean that that's the only way? No. There will often be some faster ways that involved using a K instead of a 1. All right? You guys okay with that idea? What's going on down here? Oh, gosh. Oh, boy. All right. This, I don't like this. A sub 0, the 0th term, I don't like that. So I'm going to do this. I'm going to put it in parentheses. Because, quotations, excuse me. I'm going to put it in quotations. Because how is something the 0th term? Like, what does that even mean? Well, I'll show you what it means. It means if you had a pattern that could go forwards, you should be able to trace that pattern backwards. But it doesn't make any sense to say it's the 0th term. Instead, what I would tell you is it's useful to understand what the implication is, but I will never ask you for it. It's kind of like how, I asked you what the coordinates of the removal discontinuity are, but that's literally a point that doesn't exist. So if I asked you, what would be the value, what would be like the jump off point or the 0th term, like how do you even say it? The beginning of the terms doesn't make any sense because that would mean the first term. But it's beneficial to understand it graphically. It means the pattern would have held true. It's like your plus b, your y-intercept. Let's be real here. That will never be part of the sequence, though, because it would imply the thing that happened before the beginning. Like people ask you what happened before the Big Bang, and your question makes no sense. What happened before the first term of the sequence? You go, the frig do you mean what happened before the first term of the sequence? There was nothing before the first term of the sequence. But if we follow the pattern backwards, we might be able to see. And that's all it's telling you. It's just showing you that you could write it in slope-intercept format, where the common difference is your slope. You might want to know that. Common difference is slope. You might want to write that. Common difference is slope. I think I said it 3 times now. It's the rate, since rates matter so much. And if you had to figure out what that 0th term would have been, it's literally just go to the first term and then travel the common difference backwards. It's common sense, okay? All right. It says, is this sequence arithmetic? And if it is, write a general rule. Well, the only way that we can recognize arithmetic sequence is if we have a common difference that no matter what term we go to, and we subtract the one before it, we get the exact same number every time. So technically, what we should have to do is go 17 minus 13 is 4, 13 minus 9 is 4, 9 minus 5 is 4, and 5 minus 1 is 4. Because any term minus the one before it, so we say because any term minus the term before it equals 4, arithmetic. We showed that no matter what, if we take a term and subtract the one before it, we got the exact same number every time. So D is 4, and A sub 1 is, well, it's right there. That's A sub 1. It's 1. So your general term, A sub n is 1 plus n minus 1 times 4. Could you distribute the 4 and combine like terms? Yes. So that would give me 4 times n, and 4 times negative 1 is negative 4. 1 and negative 4 makes negative 3. So these are both explicit, also known as general forms of the sequence. You just be really, really careful, because if I said that this was the explicit form, and I said, what's the first term of the sequence? What will you not say? You will not say negative 3. Negative 3 is not the first term. The first term is 1. You would have gotten the first term by using n equals 1. Just making sure you're very clear about that, okay? All right. The next one says, find the 46th term of the sequence. So let's just look. From 2 to 5 is 3. From 5 to 8 is 3. From 8 to 11 is 3. From 11 to 14 is 3. This thing is arithmetic. Once again, we have arithmetic where the common difference is positive 3. And we can see our first term. Our first term is 2. So we can just write the general form. We get A sub n is A1 plus n minus 1 times d, like that. You could, if you wanted to, distribute the 3 and get 3n, let's see, 3 times negative 1 is negative 3, 2 and negative 3 makes negative 1. You could do it like that as well. It doesn't matter which one you choose, you're going to get the same result. Let's find A sub 46. I'll plug it in here. Actually, no, I won't. I'll plug it in right there. I actually feel like it's easier to plug in here. Because 46 minus 1 is 45, And from back in my weightlifting days, I happen to know that 45 times 3 is 135. Yeah, adding plates. Because the bar with one plate on each side is 3 times 45. 135. What do you think? Crazy, scary, hard? Not bad, right? Mark? Shh. What's up? Okay. Next. You know what? Okay, I will say this, though. Something that really bothers me that I haven't seen happen in these notes, and I'm concerned because I'm going to put it on my test, is what term number has a value of blank. So if I tell you it has a value of 137, you should be able to track that backwards to tell me it was the 46th term. Now, I didn't see that in the notes anywhere, but it's going to be on my test. So you just have to know the difference between a term number and a term value. You need to know the difference. So if I say, what term number has a value of 137, you would take this formula, you would put, or this one, it doesn't matter, you'd put the 137 there. You'd add the 1 and you would divide by 3 to get your answer. Something else I never saw in the notes. N has to be a whole number. So if I said to you, is the number 139 an element of the sequence? What you would do is you would put 139 right here. You'd add 1 to get to 140. You'd divide by 3 and you'd get a decimal. And the fact that N is a decimal would tell you that number was not within my sequence. I didn't see that in the notes anywhere. Which is one of the reasons why I wanted to use my own notes instead of these. Because I feel like these are lacking. But hey, we'll see what happens. Find the 9th term of the arithmetic sequence whose first term is 8 and has a common difference in -5. Okay. Difference is -5. First term is 8. I know a sub n is then 8 plus n minus 1 times d. So find the 9th term. Mm-hmm.
When I did the math to find which term is the 137,
Yeah.
is equal 137, I got 45.6.
Did you plug it in? Where did you plug in the 137?
I did 137 equals 3 n minus 1.
So you added 1 to both sides?
Yeah.
And got 138? Subtracted. Yep. Okay. So this is going to give me that a sub 9 is 8 plus, screwed me up, -40. So it should be -32. There you go, -32. Because it's 8 and -40. I know, right? So tiring. Okay, just so you know, we get out of here in less than 3 minutes, and I expect you to be able to do the whole first set of homework questions, so, okay. All right.
What's the whole first set?
Where it says set 1.
Oh. Sorry, that was
The numbers in the sequences follow, you know what? This one says write me the rule. We've done that plenty of times. Let's move to this one. Word problems. The number of seats in the first 16 rows of an arena form an arithmetic sequence. If there are 20 seats in row 1, 23 seats in row 2, yada, 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 how many seats are in row 16? The only reason why two terms is enough is because we were told that it's arithmetic. So we know that D is 3, and we know that A sub 1 is 20. So then we can write the generic term. A sub n is 20 plus n minus 1 times 3. And it says to find the number of seats in row 16. So row 16 is 20 plus 16 minus 1 times 3. That is 20 plus 15 times 3. There are 65 seats in row 16. How about that? Easy peasy, huh? What? How do I add what? Add up the terms of a sequence? We're not there yet. Well, that'll be later, okay? No, it's not. How many did it ask you to add up, though? Like 5 things?
It says how many logs would be about 30 if there are 30 logs in the bottom layer, and the second is so long and so long until there's one top layer.
You're going to have to brute force that one. You just have to be a nerd about it.